Alright, Chem students, today we're going to talk about calorimetry. You need your blue notes packet. We're starting on the middle of page 4. Now, heat that is released during chemical reactions can be measured by a process called calorimetry. Now, if you remember, we talked about the law of conservation of energy, and that states that energy cannot be created or destroyed, only converted into different forms. We apply this law when we perform calorimetry experiments. Because of this law, we know that the heat released by any reaction must be absorbed by its surroundings. So if we remember, Q equals heat energy, and MC delta T is M equals mass, C equals specific heat, and change in T is delta T. That's the change in your temperature, final minus initial. That means that our heat released by a system equals our heat absorbed by its surroundings. We can say that MC delta T is the same or equal to the negative MC delta T. These would have to be equal to each other because energy can't be created or destroyed. It's just converted. Alright, now we need the negative sign on one side of the equation to make it equal. One side is XO and the other side is endo, so they are always opposite in sign. Now, a calorimeter is a device that we use to measure the absorption or release of heat in any chemical or physical reaction. For calorimetry calculations, it is assumed that the heat absorbed by the water in the calorimeter equals the heat released by the chemical reaction inside the reaction chamber. It is necessary to measure the mass of the water and the initial and final temperature of the water. That will give us all of the components we need for our formula. Now below we have a diagram of a bomb calorimeter. You have a very small inner reaction chamber where our reaction is going to take place, and it's surrounded by water. Now, like they said, we need to know the mass of the water being used in this calorimeter. We need to know its initial temperature and the temperature of the water after the reaction is complete. Then we can figure out exactly how much energy was released or absorbed. Okay, this is very similar to an experiment we're going to do in lab later this week. You want to suspend a can full of a known mass of water directly above the food which you're going to ignite and release the energy from. So there's a thermometer in the top of the can, and this person would have checked the temperature first. They also probably should have lowered the can closer to the flame before now. But okay, here they're going to fix it. So you want as much of that heat coming from the food that's burning to go into the can. So we want to get every degree change possible recorded on the thermometer. And it's going to take a while. Like, they have a lot of time here. Obviously there's a lot of energy stored in a single Dorito. So just imagine if you ate the entire bag of Doritos, you were going to be on a treadmill for like a month trying to burn all those calories off. Yeah, this is a pretty good, they got a good flame going here. There should be a big temperature change. Still adjusting. And no, this is not my house or my kitchen. Like, they're very messy. This is somebody that posted this online, but it's a great example of what y'all are going to do in lab later. Alright, so the energy is finally done. All of the energy has been released. We can record our final temperature and calculate how much energy was stored in that Dorito. Okay, so calorimetry, we know that heat released by a system equals the heat absorbed by its surroundings. So MC delta T equals negative MC delta T. Now the example they give us is a reaction between hydrochloric acid and sodium hydroxide that was carried out in a calorimeter. The mass of the water in the calorimeter was 150 grams, and the initial temperature of the water was 25 degrees Celsius. After the reaction was complete, the temperature of the water was 35 degrees Celsius. So how much energy in joules and kilojoules did this reaction actually release? Okay, so what we want to do, first things first, let's figure out the change in temperature of the water. Change in T, or delta T, is T final minus T initial. So that means 35 minus 25, our change in temperature was 10. So now we're going to go plug it in. We want to know the energy absorbed by the water. So we know the mass of the water was 150. The specific heat of the water is 4.18. And the change in T, the delta T, was 10. So when we plug all these numbers in and multiply them, we discover that there was 6,270 joules of energy absorbed by the water, or 6.27 kilojoules. Now we have to pay attention to our question, because our question asked how much energy in joules and kilojoules did this reaction release. So that would be the opposite of what was absorbed. So Q released was negative 6,270 joules. That's it for today's lesson, Chem students. We'll see you next time.